So let's combine the two technologies of screen recording so that I can show you anything I want from the screen, and Mathematica because, well, there's no more entertaining and rewarding and useful tool for solving mathematical problems than Mathematica. That's why they picked the name. In any case, let's take a look at the issue of making an equation dimensionless. We do this as shown right here. We want to be sure that none of the differential equation terms are bigger than order 1. If I have a dimensional equation, any given term could have any given value and I don't know how to sort it out. But if I non-dimensionalize it, the terms themselves won't be bigger than order 1. Then we're going to get some parameters showing up, and specifically a Reynolds number, perhaps a Froude number, for a different kind of problem, and then we know by the value of the dimensionless parameter which side or which pieces of the equation I have to keep. Plus, the other thing I'm going to show you here is kind of the manipulations in Mathematica. So you can read this specifically. We're in the Mathematica notebook Creeping Sphere. We're specifically looking at making equations dimensionless. And again, you could do this algebra all by yourself if you wanted to, but why not let the Mathematica do it for you. Specifically, to make an equation dimensionless, we substitute for the independent variables as shown here. So I would pick a length scale r, which is the radius of the sphere, and a velocity scale u, which is the free stream velocity, and I would non-dimensionalize the radial direction and the ur and theta with the appropriate dimensional scales there. And so, or if I just solve them the other way around, so I'm just making direct substitutions, the direct substitutions would look like this. If I'm going to do a derivative, I'd use the chain rule, so ddr would be dsdr dds, and you can see that here. But anyway, you can look at that more carefully and see if you believe it or not. What I just want to show is if I pick one viscous term and one inertia term and make them dimensionless, what's going to happen? There's many more terms in the equation, but one from each side will do it. So if my viscous term is this radial second derivative of the radial velocity, and the way you do Mathematica is you find the bracket on the right side of the term and you hit enter, which on a laptop is probably shift return. On a bigger computer, then you actually have an enter key. And so when I do that, you see I took this term and turned it into Mathematica ease. The superscripts are derivatives. This kind of looks like the real term, but it's still a little bit kludgy, but then this is a little bit difficult to interpret, but that's the form Mathematica understands. And what I'm going to do is I'm going to replace the derivative using the chain rule, and so this is the command that'll do it for me. Again, I put my cursor there. Either I can put it on the edge or I can put it in the middle. Hit enter. Again, I'll just put it right here. Enter. And what I did was make the substitution for r in terms of the dimensionless variable s. And then I'll break it into these two pieces for convenience, but that's not necessarily particularly profound. But what you see is that now the variable that I'm talking about for velocity is vr tilde. The first derivative there and the second derivative there. There's the viscosity still hanging around. There's a u for the velocity, and then r squared, and then there's one free s. Now if I pick the first inertia term, again, I'll just click on it, shift enter. Now that's what it is in Mathematica. Make the same substitution here. I'm first getting rid of the original ur all by itself. There it goes. Then I use the chain rule to get rid of the ur that's got a derivative in it. Then I've now taken care of both the things. So now let's suppose that I just make an equation that, or an expression that has the inertia term and the viscous term in it, and I divide by u and divide by mu r squared. When I get done, I have ru rho over mu multiplying this term here, which has ur and ur first derivative with respect to s. And what this is, that's the Reynolds number. And Reynolds number is multiplying the inertia term. The other terms have nothing but dimensionless quantities to it. So what I've done is I've found out that the Reynolds number multiplies the inertia terms. The viscous terms are now of order 1 and just sitting there. And so, depending on the value of the Reynolds number, I would tell you which terms I need to keep. If the Reynolds number were large, I would be keeping the inertia terms and not keeping the viscous terms. Ultimately, there's a problem with that, but we won't worry about it right now. But the problem we want to solve first, where the case where the Reynolds number is very small, for this small Reynolds number, then we can ignore this inertia term. And so in these 3 easy steps, we took the dimensional viscous term and the dimensional inertia term, used substitution and chain rule. Mathematica did all the work. And this command here is probably the one that you wouldn't necessarily guess how to do it, because it requires a derivative substitution. But that's how it is. If you ever want to substitute derivatives using chain rule, this is the command will do it. And it does it for any number, power of a variable of the any derivative, first derivative, second derivative, third derivative, whatever you wanted, it would do it there because it's just taking arbitrary numbers, and then now it's taking the arbitrary derivatives. So that would take care of it. And so that's in a quick 4 or 5 minutes or whatever it was, making an equation dimensionless.